okay, in today lab class, I will do all the steps that you have to do in the assignment part. So it's almost a repetition, but with my data set, not with your data set. Okay. So first of all, we have to upload these packages, attach these packages. You already download the data sets and save it somewhere. Okay, from Athena. And okay, I will attach these packages because we will use this one. Okay, then I already saved this file in the same folder where I open the R. And if somebody save it somewhere else, so he may use this one and browse the file and then import it into R. So it's up to you. So you may use this one. Okay, and don't worry about either the folder is working folder or not. Okay, so you can import it from here. So anyhow, my file is saved in the same folder where I open the R. So I will use the this command directly. Okay, and now I have these data sets and it contains 85-month data set. I have it, and it's about Google stock price. Okay, then if I look this data set, I have several variables. I don't need this one, this one, this one. I will play with this adjusted clause. So then I will remove the other variables. So here I will use this file name, and then in the square brackets, after the comma and the indexes for the column. So here I mention the columns in a vector, and then outside is a minus. So I will remove these columns from the file. Okay. I don't want to use that one. So now if I look my file, I just have a column for the day, and then I have adjusted clause because I have to work with the adjusted clause. So it's up to you. Okay, maybe someone else have to work with different variable. Okay, then because it's a time series data sets, so I will convert this adjusted clause into a time series data sets, and the data set start from 2016 and its first month, and the frequency of the data is the 12 because we are taking a monthly data set. So now I will save it in the same variable in the same file. Okay, but now this time, okay, first of all, when I run this one, I will just get these data sets when I haven't converted into a time series. Okay, and now once I convert into a time series, again, if I select this one, and if I look now, it will be converted into a time series data set. Okay, now the time is attached with the observations. Okay, now I will take the log. So I will save it in a new variable, log adjusted. So we did the same things, I think, in the lab 2, also in the lab 3. So here I have one new variable. Now I add it. That is a log of adjusted prices. So now I have the 3 columns. Okay, then I have to take log returns. And according to the definition of log returns is the log of current value minus log of the previous value. Okay. So then I will use this diff command. So it will take a first order difference of the log variable. And then, and you know that if I want to attach this log return with my file, this GOG, then definitely the log returns for this observation is nothing because we don't have the previous observation. Okay, then I cannot attach this one. Okay, so that's why here for the first observation, I just say it's a missing observation. Okay, you have to write this one. Otherwise, this column will not attach with your original file. Okay, because this column has a one less observation compared to my file. Okay. So now I create a new variable where I will save this log returns. So now if you want to look this file, now I have in the last column is a log returns and the first observation is missing. Okay. So that's why I put it here, this NA. Okay, the next is that because we have to check it either the log return is stationary or not. Again, I will convert into a time series, this log adjusted return. So again, I will use this variable by using the dollar sign and then mention the times and then save it in the same name in the file. Okay, before running this command, if I select this one and run this one, I just have a vector without time. And now if I run this one, and now if I look, I have a vector with time. Okay, the observation with time. So now it's mean this vector is converted into a time series dataset. This dataset is converted into a time series dataset. Okay, now I can use it in a TS plot command. So I have to plot this one, the log returns. So I can draw a zero line, horizontal line here. So what is your opinion about the dataset? Is it stationary or not? By looking this one, it's stationary. Okay. Okay, then we can check it by this is graphical way to check it, either the data is stationary or not. And then we can test it, either the data is stationary or not, by using the regular augmented equivalent test. So here I have to check the stationarity of the log returns. So, I can call this variable from the file with the dollar sign. And then, so you will see that I'm rejecting H naught, and then alternative is that the data is stationary. Okay. So the regular augmented equivalence test says that the data is stationary. Okay, now we can check it by using this augmented equivalent test, where the logs will be decided by the software. Okay, how many logs we have to use it. Okay, and then here it also at least at 5% it's less, so it says the data is not stationary with the augmented equivalent test. Okay, then the next step is that we have to divide the data set into a training and now before training and testing. Here, I have to create one new variable. I create here a new variable at time. Okay, because in the assignment we have to use the linear regression. Okay, to run the linear regression, I need an explanatory variable as a time for the linear regression. Okay, and I cannot use maybe I will show. I cannot use this date as a time as explanatory variable because R will take this one as a character variable. Okay. So then I have to create here a time variable. So because I have a 85 observations, so I will generate here data for just where is this one? Did I delete this one? Oh, it was here. So I need to close this one. Okay, now I will generate one new variable time in the file. So you know that the file name and the dollar sign and which variable you want to generate it, you write the name of that one. And then what I want to save it in here, I want to save it just the index number from 1 to 85 or 86, how many observation I have it. Okay, so you will see that here I just save this one 1 to 85. Okay, if I run this one, and again, if I look my file, I have these observations. Okay, 1 to 85. So I will use it as explanatory variable in the linear regression. Okay, so that's why I have to create this one. And then the next part is that I have to divide my data set into two parts. One is the training parts that I will use it to train the model. And then the next one is the testing part where I will test the predictability of my model. Okay. And then based on this testing part, we have to find out root mean square error. Okay. So here, first I will just show you this part. So it's mean from the original data file 1 to 81 numbers, I will use it as a 81 observation, I will use it as a training data set. Okay. And then how many observation I will use it as a testing. So 4 observations here, I have used it as a testing. Okay. So either you have to write it just the numbers here before the comma, 1, 2, if you know how many observation you have it. Okay. So here, even though I don't know the observation, so I know if I write it n row of my file, so I will get the total number of observations. So, okay, so I want to make it atomize. Okay, so that's why I write this one. Otherwise, maybe you can mention it 1 to 85. And then here, instead of this one, you can write it 82 to colon 85. Okay. So now I have a training data set and a testing data set. Okay, then I have to, according to the assignment, I have to use this random walk model. That is a benchmark. Okay. And then later we have to check it either something ARIMA model is better than this benchmark or not. Okay. So this is the benchmark. We have to use this one. Okay. So here in the ARIMA, I will use a log of close. So here I'm not using log returns. Why? In ARIMA, we have to use stationary data sets, and we know that the stationary data set is log returns, not log of adjusted. Because here I am using 1, so it's mean this ARIMA command will automatically take the first difference of this log of adjusted, and we will get the log returns. Okay. So inside we are using the log returns. Okay. So that's why I give this one. Okay. So, and then here drift is true main. I want to include the intercept. Okay. Here for the P and here for the Q. Okay. So if P and Q are 0, then it's mean we are using a random walk model. Okay. So now I have this one. Okay. Then the other way of using this one, I already told you that maybe you can use here a difference is equal to 0. And then you use this one as a log return as original variable, you can use it. But I don't want to prefer this one. Okay. Then you have to do a 2-time retransformation from log returns to your original variable. Okay. Because if you give the model this variable, the model will give you the output in the same variable. Okay. If you give the model to this variable, it will give you the prediction in terms of this variable. Okay. So even though I don't think you will use the second difference, but if let's say I have a stationarity of the data set after taking the second difference, so same, because this data I will use it to take the second difference. So I will use this one, and then here I will put 2. Okay. So it's very easy then to transform back into a original data set. Otherwise, you have to do 1, 2, 3, 4 steps to transform it if you want to use it, the data set after taking the second order difference. Okay. Then it's harder. Okay. So I will prefer this one, and I will recommend you also, you have to use this one. Okay. If you have the second difference, first difference, you mention it here. Okay. Now we have the output from the random walk model. And here is the summary. We have a AIC value, AICC, BIC that I can use it for the comparison. Okay, yet I haven't other model to compare it, but we can use a comparison purpose. We can also use this one as a comparison purpose, which model is a good for the training data set. Okay, not for the testing training. And then we can also check the confidence interval, testing of hypothesis. This drift is not significant here. And then I will also use this check residuals, because this one is a benchmark model. Then I will use also check the residuals. Either the residuals are white noise, there is no autocorrelation, it's approximately follow the normal or not, or maybe you can use the normality test for the residual. Okay. But I will not do this step later for every model. Okay. I will just use this command only for the model that are potentially a good model. Okay. Because we have to test many models, but I will check only this command. I will use it for the models that are potentially good one. Okay. So here loop box test says that there is no autocorrelation. Okay. Okay. Now, after having this random walk model, we have to fit the linear regression. So I will use this LM command. Here you don't need to write even the formula. Even without that one, it will work. So you have to write here a dependent variable, and then this tilde sign, and then how many independent variable, you have to write it in the plus sign. So you have only the one independent variable. So here I will use a time, and then these variables are available in the training data sets. So I have to mention the data sets then. Okay, and then I will save this output from the model in this regression variable. So once I have the output in this one, if I write the summary, then I will get the output. Here is the intercept, slope parameter. Intercept is significant, and the slope parameter is significant. Okay. Okay, now I have used this model from I trained this model based on first 81 observation. Okay. And then let's say I will check it, what is the prediction based on this linear regression for observation 82 to 85. Okay. So then I have to create a data set here in a new file. I will write a data.frame and time is equal to this one. Okay, now if you want to check this one, so here I create a time variable from 82 to 85. Okay, and then I will use it here in the predict LM command. Okay, I want to predict it for these observations. Okay, I already trained my data set based on the 81 observation. So then here is the model where I save the result. And then based on this model, I want to predict for these observations. Okay, that I save it in the file. It's 82 to 85. And then I will save the result in this variable. So here I have the prediction for the linear regression. Okay. And then I will plot the first 85 observation. I will plot the 85 observation. So it looks like this. Okay. And then I will plot the, here you will see that I will just plot the first 81 observation because the model is based on 81. Okay. So this is the, this line I will get it when I get the fitted value from the models. Okay. Based on my observed data set. That is a training data set. So that's why here it will stop up after 80 until 81. Okay. So these are the observations that I missed it and take it as a testing data set. Okay. Okay. Now I will use it as the line for 82 and 82 to 85 observations. So these are the 82, 83, 84, and 85 observations. These are the original observations. Okay, then I have already a predicted observation from the model. So if I draw that one, so I will get the prediction here. Okay, so graphically, if you look that one, the prediction from the linear model is not good. Okay, so maybe you can also check it with the root mean square errors. Okay, But anyhow, this is not good. We are quite away from the testing data set. Okay. Okay, then the next step is that because we have to find out the root mean square errors. So now I will create a file where I will save the test data set, forecasting data sets, and the difference between the test data set and the forecasting data set. Okay. So here I will just save the forecast values. The error terms are the error in the forecast. So here is the original testing data sets, and this one is the predicted values from the model. So the difference between them is the forecasting error. So I will save this one, and then I will create a data frame where I will combine C bind mean. I will combine all the columns, whatever the columns I want. So I want the original one, test data set, the forecasting data sets, and then the difference between these two variables that I already save it here. Okay. So I want this one to be combined into one file. So here I combine it. And if I want to check this one, so you will see that this one is my testing values. This one is forecasting values. So these four values are these one. Okay. And these original are the testing values are this one. Okay. And then this is the difference if I take the difference from this values to this values. Okay. So this one is the numerical difference here. Okay, then you may label this one here. I have a different names. So you may label this one. The first column is the testing data set, and the second column is the forecasting or the estimated values from the models, and the third one is the residual or the forecasting errors. Okay. So you can assign the names here. It's possible. Okay, then the next step, actually you have to do it, but I did it here. So in order to find out whatever the prediction evaluation criteria, you have to use it. So I will use this one. Okay, you can use any of this one. All these criteria are available in this package. Okay, so I will first attach this package in AR, and then I will use this command, root mean square errors. So in this command, I have to give it the original data set, that is the testing data set, and then I have to give it the forecasting data set. Okay, so these two columns I have to give it. Okay, and then I will save the result here. So this is the root mean square errors. Okay, you can find out some other criteria like here. So it's up to you. Either you can write it by your own commands. It's very easy. So, and either you can use this package. Okay. So if you put the cursor here and press F1, here is the help. Okay. You have to give the actual values. That is the testing value. And then you have to give the predicted values from the model. Okay. Once you give these two columns, then it will automatically find out the root mean square errors for you. Okay, but there are many others criteria is also available like absolute errors, average precision, like absolute percentage errors. So lot of others criteria are available there. Okay, so maybe you can check it. Maybe something others might be this one, might be this one. Okay, so it's up to you. Yeah. I will check it. Either the LE is the still the root mean square error, or it's a different. I have to check. Root. Okay, this one is the different one. Then I think it's not L. I can use this one. If I press F1, yes, I have this one. So yes. Then we have, yeah, thank you. So it's without L. Okay. But there are many other criterias are available. You can use that one also. Okay. So this is the one things you have to find out, and then at the end of the assignment, you have to summarize this criteria for each model. Okay. For the regression, for the benchmark model, and then for the Holt exponential model, and then the selected ARIMA models. Okay, that are potentially good model for the data set. Okay, then after that, we have to fit this Holt exponential model. So we already did this exercise in lab 2. So I will use this variable, I use this command, Holt, and then how many observation I have to predict it. I have to predict it for observation. Here I will use exponential is equal to false. Okay. Maybe someone say it's a true, then you can check it either with the false, you get a lower AIC, or either with the true option, you will get the lower AIC. Okay. Maybe use that one. Okay. Okay, I will use the here a false here. And here is the summary result. We have a AIC, VIC values. Here is the forecasting values. Okay. And here is 80% confidence interval for these forecast values. And then we have the 95% confidence interval. So if you plot this one, so until here, I use this data set as a training data sets. And this one is my testing data set here. Okay. So now I will check it. I can also display my forecasting values. That is this one in the graph. So here I can use this one because I already saved this one here. No, this one is the original values, and this blue one is the forecasting values. Okay, so at least this Holt exponential smoothing model is better than this regression. Okay, without looking the root mean square errors. Okay, at least the first observation is very close, the prediction, and this one is far away. This one is a little bit close, and then this one is far away. And definitely, if you find out the root mean square errors here, the root mean square error is bigger compared to the here smaller compared to the regression. Okay. Okay, then the same things that here I will save the forecast values from this model into a one new variable here, and then here is the testing data sets minus the forecasting data sets. I will get the forecasting errors. So I will save it this variable. And then I will combine all the important variable, the original data set, here the forecasting value, and here the forecasting errors. Okay. So I combine them by using the cbind command and then save it in the data frame. So if you look this one, we have this one. And then maybe you can change the name. The first is the testing data set. Here, this one is the forecasting, and here is the forecasting error from the Holt exponential smoothing model. So here I just change the names. And then after that, here you have to calculate the root mean square errors. Okay. So I don't need to use this one because I already attached the library. So again, here I have to remove this L. So root mean square error, I will use this command. I already save here the original data set. So this one is the original data set. And then in the same file, I save it the forecasting value from this Holt exponential smoothing model. That is this one. So I have to give these two things, forecasting and the original. That is the testing data set. And then I will get the root mean square errors. Okay, you have to save this one, and at the end, as a summary, you have to display in the assignment. Okay. And which model is the good one in terms of forecasting? You have to check it, the root mean square errors at the end. Okay. Okay, now we have a benchmark model that is a random walk. And then we fit this regression model, and we fit this Holt exponential smoothing models. And then according to the assignments, we have to search, I think, 3 other maybe ARIMA model that is a good one. Okay. Out of many. We will try many, but we will just select just 3 models. Okay. So okay, before selecting the good ARIMA models, so first I will just use this ACF plot. So here I just use this lag 12 because we are using the monthly data set. So yes. Yes. Okay, if you have a problem, just put the cursor here, press F1, and then it says from which package you are using. Actually, I am using this one, forecast. Okay, so this one is from this one. So capital ACF is from this one. So it's 6 observation for what for this ACF plot. So maybe it's by default, it will give you the 6, but I think if you look inside the commands, there is an option how many observation you want to display. Like here, if I miss this one, so then software automatically display the optimal one. Okay. So because I know I'm using this monthly data set, so the annual frequency is 12. So we are interested in the 12. Okay. It's not logical that current price is related to the previous year some month price. Okay. Okay, now we have this ACF plot, and then we have a PACF plot. So did you find something like here in this table? And we haven't found this tail of exponentially from ACF plot. Okay. And we haven't found this one in a PACF. This one is from PACF plot. And then we haven't found these two things in the both plot. Okay. So it's mean we are not in the situation here in the table. Okay. And then if I look this one, this one is close to the significant. It's 11 month. And then here again, it says that it's 11 month is significant. Okay. So it's mean the current prices might be depends on the 11 month ago prices. Okay. But then you know that in your case that we have the financial data set, we are not expected this thing is logical, that the current stock price is linked with the 11 month ago prices. Okay. So it could be logical for me if it is a 1 or 2 lags is significant. Okay. Might be 3, but not more than that one. Okay. Okay. Then I will start the biggest model, that is 414. So first I will start from here, and then I will simplify this model and then try to figure out which one is the best model. Okay. So for the assignment purpose, I will not say that you will start it from 1111. Okay. So start it with the 414 and then try to simplify that model by looking the output and the significance about the parameters of your model, the terms in your model. And then you simplify that one, and then you look which one is the potentially good model for you. Okay. And then choose that model. We have to choose 3 models. Okay. Maybe Andrew, you want to say something about? Yeah. Okay, now I will start it from here, and you will also start it from there. So I will start it with ARIMA 414. Okay, and here you will see that I haven't used any command to check the residuals. Okay, so I only check the residual command. I will only use the residual commands for the models, which one is potentially good model. Okay, then we have to check it either if the assumptions about the residual also are fulfilled or not for that model. Okay, here I have this model, and you know this command, and drift is included here. If I run this one, I have the summary where I have this AIC, AICC, BIC that we can use it for the comparison. Okay. You can also use this one also for the comparison purpose between the two models if you want to decide which model is the good one. Okay, then we have to check it the significance of the coefficients here. So there are 4 AR terms and the 4 MA terms. And then one AR terms is not significant and one MA terms is not significant. Okay. And then we have to check it which terms have the highest p-value. Okay. So if you look, this terms is highest p-value. So this terms is like less important for me compared to the other ones. Okay. That is insignificant. So first of all, I have to remove this one from the model. Okay. And now, so I have written here, one AR and MA terms are not significant. And then I will just remove this one because this one have the highest p-value. So I will remove it in the next step. I will remove these terms from the model. Okay, then if I remove one MA terms, so then I will get a 413. Okay, because I have to remove one MA terms. So I have to reduce one Q, okay, not P. So now I will fit this model and then again I will check the output. So what was the previous AIC? And so the previous was this one. And now the current is around 200. And then if you check it, let's say only this one is 0.603. And what about the previous one is a little bit lower than this one. Okay. Okay, then we check it the significance. So, okay, you will see that if I remove a one terms from this previous model, so here it looks like some more significant terms here with the low p-value with the 3 steric. So if this one is the good model, if I remove something here, I might expect that there should be a more significant here terms. Okay. So even this, if I look just the p-value, it becomes more worse model. Okay. So again, I have to check it which terms are non-significant here. This one, and which one has the highest p-value. So this time AR2 terms have the highest p-value. Okay. So it's mean this time I will remove one p-value. I will reduce it. Okay. So one AR terms I will reduce it from the model. Okay. Now I will fit this 313. Again, get the summary. Little bit improvement from the previous AIC. Okay, then I have to check it the significance here. Again, some terms are non-significant here. And now we have to check it which terms have the highest p-value. So this one have the highest p-value. Okay. So now this time I will remove this MA terms. Q. I will reduce the Q. Okay, then I will fit again this model. Check the summary. So even this, after removing the one terms, this looks more worse because there is a less significant terms in that model. And again, I have to check it, okay, out of the non-significance, which one has the highest p-value. Okay. Again, it's MA. So you will see that next I again reduce a one MA values. Okay, one Q I will reduce it. Okay, now I will fit this one. Again, I will check it the summary. So even though I have a many non-significance here, and then what about the AIC? AIC is 197. You can also check it with this BIC also. Okay, it's not like exact that you have to check it AIC. Okay, might be some models good with the BIC, and then might be you can check it based on the prediction then. Okay. Okay, now if I check this one, the coefficients. So I have a non-significance. Many of the coefficients are non-significants, and then this time I will reduce a one AR terms. Okay, so I will reduce a one P because this AR terms have the highest P value. So now I will reduce it one. I already fit this one. Okay, now I have to reduce this one. So it's become 2. So now again I will fit this one. This time this drift terms become significant at 5%. And still I have this AR2 terms is non-significant. And what about this AIC? It's little bit improved from the previous one. And now by looking this one, I will remove this one AR terms from the model. Okay, then I have this 111. Okay, now I will check this one. So this is significant. This is significant. And then MA terms is not significant. And what about the AIC? It's around 200. Okay, so the models that have the more coefficients, when I use it, it was around, I think 203. Yes, this one. So even I have a very less terms in this one, there is not too much reduction in the AIC. It's around 200. Okay, now I will check also the residual of these models. Okay, so might be this one later we will discuss combinedly. Might be this one is potentially good model. So I will check it. The testing either the residual are not autocorrelated. Yes, not autocorrelated. And no AIC value for the residual is outside the bound. Roughly, I can say it's approximately normal, but you have to test it if you cannot say something exactly from the models. So it looks like that the error terms is the white noise. Okay, now from this model, again, I have to check it which terms I can remove it. No, I will remove it one MA terms. Okay. So I will remove one MA terms. And now I have this model. Again, if you check it AIC, it's little bit improved. Okay. So this might be a potentially good model, this one. When I started from the 414, it was 203. Okay. And here, this model is a very simple one. There is no too much reduction in the AIC. But when you check it in terms of the prediction, you will find this one is a better than 414 model. Okay. I haven't found out the root mean square errors, but you can try that one. Okay. And here, let's say check the significance. Only the drift is significant. This is not significant. And then because this, I will say that, okay, this one might be a potentially good model with the less terms and almost the same AIC that have the model with the more terms. And then that's why I will check also here the residual test. No autocorrelation. This might be significant here. It looks like approximately normal, but you have to test this one by using this Anderson-Darling, whatever you test, you have it. Okay, I explained it, I think, in the lab 3. Okay, now I already told you in the exercise, and I think you have it from the lectures. You always have to fit one is the benchmark model, that is a 0, 1, 0. And then the other simplest model, you always have to fit it 1, 1, 0, and then 0, 1, 1. Okay, that model you always have to fit it. Okay. So I will not say I will remove this one, but maybe you can also check it. I have to remove this one. Anyhow, even though if this term is significant, I always have to try the other one. Here is 1, 1, 0. Then I always have to try 0, 1, 1. Okay. So I told you in the lecture also, you have to check always this one. So that's why I will test this one. Here, almost the same. AIC, that one is the previously model. And then their coefficients. This is significant and this one is not significant. So the same things happened in the previous one. Both have almost the close AIC. And then because this one might be a potentially good model, so I will use this one. Residual check, no autocorrelation. Here is this one might be it's randomly. So looks white noise error terms. And then approximately normal, but maybe you can check the normality by extracting the residual columns and then apply the Anderson-Darling test or maybe Job-Bara test. So it's up to you. There are many tests available. Okay. Okay. Now, based on the above output, this one is the benchmark model. Okay. So I always have to include this one. And if you look the benchmark model, so here I will just combine the 4 models that are potentially good model. Okay. So we always have to combine, use this benchmark 0, 1, 0. Okay. So I will extract their AIC value. So this is AIC value for the benchmark. And then I have to use the AIC value for 0, 1, 1 and then 1, 1, 0. Okay. That is this one. And then, so here I using the BIC value, not AIC, but it's up to you. Either you extract the AIC, BIC, you can use any criteria. It's up to you. Okay. So here I just extract the first, these potentially good models. I use this one and combine their BIC values here. So which model is the good one if you check this one? Which one has the lower BIC value? So I use the BIC here. Okay. So if you look on the based on the BIC, your random walk model is the good one. Yes. Now, if you have a complex model, and let's say that give you the AIC values is 203. And if let's say you are using the random walk model, that is a very simple model, and that give you the AIC to 201. So if you check the forecasting, you check it your forecasting. Definitely, I know that this random walk will give you the less mean square errors. Okay. I mean the forecasting mean when you check this part, when you make the graph like this. This is the predicted one, this is the observed one. And when you check the root mean square error based on 414 and based on all these simple model. This simple model, they have a quite close AIC compared to this 414. There is no too much reduction in the AIC. And then this simple model, later you can check it. I will not calculate all the root mean square error from the model. But if you think that 414 is a good model because their AIC is less, then you can check this prediction by using the root mean square errors. So I know that this simple model gives you the better prediction compared to the complicated one. Okay, even though their values are very close, both the complicated one and the simple one, you will prefer the simple one and not the complicated one. Okay, so might be the complicated one may exist the overfitting problem. Okay, so you will prefer always the simple one. It's not only the AIC. Let's say here the AIC for 414 was better. Okay, but it also contained many non-significant terms there. Okay, and then okay, if you have the doubt, okay, I have to just decide on the AIC. Okay, let's say 414 was the good one. Okay, because it says the minus 203. Then there are something more. you have to test it. Then why not you check it, the 414 predicted values. Let's say these are the predicted values, and these are the observed values in the testing data set. And then you find out the root mean square error. So I know that the complicated one that you say that is the best one, it is the worst one compared to this one. Okay. I haven't checked this one, but I know I checked this one. But you have to do this one by yourself. Okay. So I will not prefer the complicated one where there is a little bit improvement in the AIC. So even I will prefer the simple one. There is a little bit less improvement compared to the complicated one in the AIC, but it's close to the complicated model AIC and where the prediction is better. Okay, so I will prefer that one. So here I choose this all the simple models. And once you check this root mean square errors, when you check the difference between them and use the formula, you will always get the minimum answer here. So these are model are more better than the complicated one. Okay. And then again, in the complicated one, there are many non-significant terms. Here we also have the non-significant terms, but only one, and it's very simple. Okay. But anyhow, at the end, we have to choose some best model, even though all are non-significant, but we have to choose the last one, best model. Okay, now based on the AIC, I can give the favor to this one. Okay, because this one is the lowest BIC value. Here I calculated the BIC, but I know once you calculate the AIC, this model would be better. Okay, here I calculated the BIC, and based on the BIC, the random walk model is the best one. But when you calculate the AIC, I know that this model will give you the better result. Okay, then might be then you can compare their prediction ability based on the test and the forecasting. So you have a test data sets, and then you have forecasting data set based on this model and based on this model. Okay, then you have these two values and find out the root mean square errors. And then if the root mean square error of this model is lowest compared to this one, then I will choose that model. Okay, because that ultimate my goal is the prediction. Okay, I just choose the potentially good model based on AIC, BIC. So might be there is a conflict in the decision. AIC says that this model is the best one in the potentially selected good models. Might be BIC says that this model is the best one. And then at the end, because our ultimate goal from the assignment is that we have to predict. Okay. And then we have to check it which model is the good one in the prediction. Okay. And then we check it for the prediction part, we have to check it root mean square error. Where the root mean square errors for the prediction is the less. That model is the good one for us. Okay. That one is the final model for us because ultimate goal is the prediction. Okay. So I know that this 414, even though its AIC is a little bit lesser than this simple model, but they are very bad in the prediction if you find out the root mean square errors. Okay. Here I just find out the BIC, but once you calculate instead of here BIC, if you write a AIC, I know that in the AIC, this model is better. Okay. I test it, but I haven't write it here. Okay, now here I create a function because now we have to retransform the variable into original one. Okay. Once you have to do check the forecasting ability, you always have to transform your prediction from the model into original variable. Okay. And then you have to find out the root mean square errors. Okay. So our original variable is just without log. And then we use in all the model in the ARIMA, we use the log of the stock prices. Okay. And then we have to take the exponent of that part, and then we will retransform it into original one. And then we can find out the root mean square errors. Okay. If you do these things without transformation, it's wrong. Okay, your original variable is without log values and your prediction is in terms of the logs, because we use a log of stock prices in the model. So model will give me the output in the same variable that I use it into the model. Okay. So then here I create this function. So here you just have to give this forecast value, and it will take the exponent of that values and retransform it into a back values. And then if you have the confidence interval, so let's say I will show you first. Where is that? I will show you here the output first. Okay, not from here. Okay, might be the output for any of the model. Okay, let's say for this simple model, when I find out the this coefficients, so now yes, and then I haven't show it here the confidence interval. So did I show somewhere a confidence interval? I think I have it for the simple model. Yes, for this one. So here you have the confidence interval, but that confidence interval is based on the log of prices. Okay. So if you want to convert into a confidence interval back to the original variable, you have to take the exponent of that values. Okay. And then it will be transformed back into a confidence interval of the original variable. Okay. So that's why in the function here, here I just take the exponent of the forecast value. It will retransform into original variable. Okay. And here I just take the exponent of the upper part. This is the upper part. And then here I take the exponent of the lower part. And we have this one. Okay. And then you can retransform it, the original, the log values into transform back into the original values. And similarly, the confidence interval for the log values retransform back into the confidence interval of the original values. Okay. So this now I will use my potentially good model. So my good model was this one, the best model based on the BIC. So first I will forecast it for the four values based on this model. So this will give me the forecast in terms of the log of the stock prices. Okay, because here in this model, we give the log of the stock prices. Okay, and then we use a D is equal to 1. So we have this one, the forecast values. Okay, and you will see that it's a small values because the model give me the prediction in terms of the log. Okay, and then we have to retransform back into the original one. So then I will use this function, this above function, and the required things is that here you have to give this forecasting from the model. So if you give this one to this function, and then if you see this one, it retransform it. So this one is the forecasting values in terms of the log. So it takes the exponent of this part and then will give you this one, the original values. This is the lower and upper confidence interval, 80% confidence interval for the log stock prices. And here is the, when I take the exponent of this one, when I take the exponent of this one, it will retransform the confidence interval of the log prices in terms of the original prices. Okay, similarly for the 95% confidence interval. Okay, so the main thing is a function is not difficult. So the main thing is that you have to take the exponent of the values, whatever you want to transform it. Either it's a confidence in limits or either it's a forecast values. Okay. And now, okay, now I can plot this one. So this is the forecasting values. Okay. And now I can plot the original values, and you will see that with the 0, 1, 0, if I just look graphically without looking the root mean square errors. So this is quite close, and this is quite close, little bit away, and this forecasting value is more away from this one. This one is the original value, and here is the forecasting value. Okay, but anyhow, this one is the graphical one. You have to quantify its how much the difference is, that one. So then we will use this criteria, root mean square errors. Okay, so you have to find out the root mean square errors for these models. Okay, and then here I will just I did before. I will just combine the prediction errors, and then I will combine everything here. Forecasting values, original values are actually the test values, forecasting values, and here is the forecasting error. That is the difference between these two values. And then you can give it some names. It's up to you. And then at the end, once you have this one, again with the package, you can use this root mean square error command, where you give it this column, the actual values, and this columns, the forecasting values, and then you will get the root mean square errors. Okay. So similarly, you have to do it for the other potentially good model, that is 0, 1, 1. So you have to do the same things, make a plot here. So this value is quite close, but the other value is a little bit away. But I cannot quantify this one. Either this one is the best one or the previous one is the best one. Then you have to find out the root mean square errors. Okay, I cannot say something based on the graph. Okay, you need some numerical values. So again, you have to retransform into a original variable, the forecasting, and then you have to find out the errors, forecasting errors, and then you combine all the relevant variables, and then you have this output. And then here I haven't found out the root mean square errors for this data set, but you have it here. Okay, use the same things down and check the root mean square errors. Okay. Similarly, you have to check the root mean square errors for the other potentially two good models. Okay. So I just calculate the root mean square errors for 0, 1, 0. Okay. And then at the end, you have to summarize it. Which model has the less root mean square errors? Okay. And that one is the good one in terms of the prediction. Okay. Okay. Now at the end, okay, which one is the good model? For the good model, you have to check all the assumptions. There is no autocorrelation problems there, and might be the error terms follow a normality. Error terms should be a white noise. Okay. And then at the end, for the good model, I think it's also in the assignment, you have to check it either there is no arch effect in the residuals. Okay. So it's mean the error terms are not heterostochastic. Okay, the variance over the time period for the residual is constant. We want this one. If there is a violation of this assumption, then I will go for the arch model. Then I will not use this model. Okay, because this model will not accommodate this problem. Okay, so because I expect that this 0, 1, 0 is the good model based on the prediction, but you have to check it. Okay, I just find here a root mean square errors only for the 0, 1, 0 model. Okay, you have to check the other models and then make a one table and summarize it all the for the prediction root mean square errors. Okay, and then figure out which one is the best model. And for the best model, you have to check this one, the arch effect. Okay, but you already done the other assumption part, like there is no autocorrelation by using the loop box test, and then you can say something based on the normality based on this histogram, or maybe you can use some normality test. In the lab 3, we did this one, maybe Anderson-Darling test, maybe Barkujara test. Okay, there are a lot of tests available for the normality. Maybe you can use one of them. And then you have to check the arch effect. Either the residual variance is constant over the time or not. Okay. So because in this for this data sets, this model is the best one, that is a random walk model. So I will check here the arch effect. So the null hypothesis that there is no arch effect. So it's mean the variance over the period for the residual terms are constant. Okay. So there is no violation of this assumption. Okay. Then you can also check it for the other potential model. Either this assumption is violated, p-value is the highest one, highest, more than 0.05. So it's mean we do not reject H naughts, and our H naught is this one, no arch effect. It's mean the residual are constant. So model fulfill that assumptions that the variance of the error terms are constant over the time period. Okay. But if this assumption is violated, then we will go for the arch model. Okay. We will not use this model. Yes. Yes. Then we do not reject H naught. H naught. If p values is less than point, whatever the level of significance you will use, then it's you will reject H naught. It's not only for this one, it's for every test if you use a p value. Then it's mean over the time period, your residuals haven't have a constant variance. Okay. And then if they don't have the constant variance, then we have to use arch model, not these models. Now, for the assignment purpose, you have to stop there and just make a conclusion that there is a arch effect is present in the residuals or not. Okay. And then for the exam, I think you have to check it with the lectures. Yes. Uh, here, all the these are the BIC. Okay.
So here, when we look at this plot, we see that we basically accept that this highlights the 6, which is quite highlight. We might expect one to have 2 if you want. So that way, it's not surprising that for all models, there's a lot of work with a lot of tables, but it's something that they are applying away, not good. Significant close to it. Then your running up doesn't necessarily will be 0, 1, 1 or 1, 1, 0. It might be a model close to where the king is. That's why there are so many different equations. But here, looking at it, immediately predict that you disregard this higher that your best model has happened to us. So that way you make an exam of all the assignments and do several hours work, but you know where it works.
Any question?
Perhaps I immediately I will tell that. Thursday morning, deadline, or some extra commands to go. So I think that like many of you asked me about this from the computer lab number one. That would be for perhaps a good idea if I like close this. Runs the biggest problem.
So, okay, one thing is that even you can work without defining the work directory, okay? Because basically you have to import the file into R first time. And then in the script, then you have to write your commands, okay? So I will say that, okay, even though without declaring the folder, my folder, this one is a working directory, you can use this one. So maybe you have this CSV file, yes. I think this one is more for CSV. Here you will see that we have the commands for CSV. Once you do these things and then copy this one and run this one, and you will get the data set. They have the CSV, but they have something else. The first one is just like a read dot table. If you go this one, here I have to give it, okay, it might be. So then here, there are a lot of other things, other type of files here, encoding. So this first command is just like a read dot table, I think in AR. That is a journal one. You can either read a CSV file with different separator operation, maybe comma, maybe semicolon, maybe tab command, or maybe some other type of files. Okay. But this, the lower one is only for the CSV.
But if I use this and it's automatic.
If it is read the, I don't know by what is the by default. Okay, okay, by default is a comma separator. So CSV is actually the comma separator. So no problem. Okay, but the second one is especially for the CSV. Okay, so one thing is that either without declaring this folder as a working folder, because you just one time you have to do it, like you have to import the file into R. Okay, and then might be I will use this one. Let's say for this. First, I will import the file here. And then here you will give it the name, whatever the names you want to. Maybe I will use it like maybe. Okay. So at the end, I will get this name when once I import it, the data set in the into R. Okay. Once I import it, and you will see that here I will get this file, and the name of the file is this one. Okay. So then next, all the commands I will use it by this name. Okay. Then we don't need to be declare the which one is the working folder and which one is not working folder. Okay. Then the next is the thing is that if someone want to declare it working folder, so here let's say because I open R in the folder where the data file is available. So you will see that here I just write it read.csv, but here I just write the name of the command, the name of the file. Okay, but I didn't mention any path. Okay, so it's mean here currently if you look at here, the once you look in the file tabs, so I will see my data set here. So it's mean this folder is already a working folder for me. Okay, but sometimes if this is not a working folder, then
So, because what he does, and this is absolutely correct, that he opens after file is uploaded, then he opens all the images from there. That's why he automatically gets the working directory which he wants. The majority of you open are single separately, and then if you put command this get wd it's not done documents. And that's why you messages start.
Okay, you will see that here because here lab 4, because here my folder contains dataset and my folder contains R files. Okay, so I open R from that folder. So that's why.
That's why they are going to open our studio.
Mhm.
And when they open, I think if you just close the studio, then open our studio, then directly on search.
Okay, I will just. I will also stop this one.
Where you are, so the directory won't be done. But this thing,
Yeah, it's good.